So last week we talked about two big ideas. We talked about exponential functions and we talked about inverse functions. So exponential functions were functions that we raised some number to an exponent and the exponent was a variable. So we ended up with this repeated pattern of multiplication. Then we talked about inverse functions. Inverse functions were functions that undo one another, right? Addition and subtraction, multiplication and division, square roots and squares. Well, what we're going to talk about this week are logarithms. Logarithms are the inverse of an exponential function. The answer to a logarithm is the exponent to which that base must be raised to obtain a given value. So let's just take a second here and look at this part of our notes. When I have an exponential function here, I know this is exponential because I have an exponent that is a variable. I can convert that to a logarithm. So what I want you to notice here is that when we convert from an exponential form to a logarithm form, these are the same exact expressions. They have the same value. This says b raised to the x power equals a. So when I multiply b times itself x times, I get a as a result. Logarithms are kind of the opposite. They say a is the result when I raise b to the x power. Okay, so make sure you really highlight this in your notes, converting from exponential to logarithmic form. Okay, so both equations have a b as a base and x and a y. They're equivalent, so here's a few examples. B to the e equals n. That's the same as the log base b of n equaling e. That's a little abstract, but maybe let's look at the next one. Here we have 3, let me grab my highlighter, 3 to the second power equals 9. Well, in logarithmic form, we say 3 to what power equals 9? Well, it must be to the second power. So let's look at a few examples here. On number 1a, I want to convert this to logarithmic form. Well, here's what I do. I know that this is going to be a log, and that the base of the exponent will be the base of my logarithm. I know that the answer is an exponent. So the 16 must go right here. So the way we would read that is that log base 2 of 16 equals 4. Why is that the case? Because 2 to the fourth power equals 16. Let's look at another example here in part B. Here we have a base of 4, so we're going to write this as log base 4. I know that the answer is an exponent, so this will be negative 3 here, which means that I'm going to put 1 over 64 right there. Why does that work? Because 4 to the negative third power is 1 over 64. Last one here, we're going to rewrite this as the log base 10 of 1/10 equals negative 1. Now you may have noticed, let me clear that up a little bit. Let's get the eraser out. Let's make this negative 1. So what you may have noticed on this one, I didn't write a base, okay? Think about when we write a square root. When we write a square root, we usually don't write the index 2, we just write a square root. Well, that's kind of the same here. 10 is what we call the common base, okay? So if a base of a log is not given, we assume it's 10. This log here is 10. I can write it, that's no problem. But if you ever see a log without a base written, we assume that it is log base 10, the common log. So that's the first three going one way. Now we're going to go the other way. I find these to be a little bit more intuitive. So what we want to do is we want to write this in exponential form. Well, the base is going to be the base of my exponent. The answer is the exponent is an answer. So this 3 goes here. And I can always check my work. Wait, 2 to the third power. Yep, that's 8. I'm good. Over here in example example B, I write the base first. The base here is 10 to the second power is 100. And I know that 10 squared is 100, so that works. And finally here on example C, I'm going to write this as 10 to the negative third power equals 1 over 1,000. So all we've done so far is we've moved back and forth between logarithmic form and exponential form. Now we're going to take a minute or two to just review our exponent properties. Like I said above, logarithms are very closely related to exponents. So if exponents and logarithms are very closely related, it makes sense that the rules that govern exponents will also govern logarithms. So just a quick review here. I have some rules that we've seen at least a couple times this year. The product rule. When I multiply common bases, I add their exponents. The quotient rule, when I divide common bases, I subtract their exponents. And the negative exponent rule tells us that a negative exponent creates the reciprocal of the positive exponent. So b to the negative n is the same as 1 over b to the n. The power rule, when I raise an exponent to another exponent, I multiply those two exponents together. The expanded power rule basically tells me that when I have parentheses, the exponent belongs to everybody inside. Finally, the zero exponent rule tells me that anything raised to the zero power is 1 as long as x doesn't equal 0. So right at the bottom here, there are 3 examples. I want you to pause the video here for a minute and try these 3 examples. I'm going to work them out completely and walk through them together. All right, let's check our work. So on number A, I'm using the power rule. It's really the expanded power rule. That fourth power exponent belongs to both members inside the parentheses. So I multiply 3 times 4 to get 12 here. And then I multiply 2 times 4 to get 8 here. And I'm done. So over on part B, I group my variables together. I know that my A's are going to come together and my B's are going to come together. I first multiplied a to the 4th times a to the 2nd, and that's where I got a to the 6th. And then I let a to the 5th stay in the denominator. In red here, I multiplied b to the negative 5th. Well, I made that positive 5 in the denominator using my negative exponent rule. So I ended up with b to the 8th over b to the 7th. I simplified each of those fractions, and I got a times b. Over here on part C, I simplified my 0 power. Be careful. This 0 only belongs to the a, not to the 2. Then I applied this exponent to everybody inside the parentheses. I rewrote my my product as a fraction to get rid of my negative exponents, and I found that I had 2 over 16 times a to the 6th. I simplified my fraction for a final answer of 1 over 8 times a to the 6th. Let's move on to the next page here. What I wanted to try to do here, we're going to evaluate using exponential rules, okay? We're going to evaluate using exponential rules. So, example A here, and number 4, example A, this asks me the question, okay, right? Logarithms ask me a question, 6 to what power equals 36? Well, I know that 6 squared gets me to 36, so my answer on part A will be 2. Part B asks me 10 to what power equals 1,000? Well, I know 10 squared is 100, and 100 times 10 is 1,000, so this must equal 3. Over here, I'm going to write this as 2 to what power equals 1 over 16. All right, now fractions have showed up to the party, so we're a little bit more complicated. But all that really tells me is that my answer must be negative, because negative exponents create fractions. 2 to the, and now I'm really trying to figure out 2 to what power is 16. Well, I saw that a little bit earlier. 2 to the 4th power is 16. So log base 2 of 1/16 is really negative 4. Down here on part D, I know that 4 to what power is 1 over 64. Well, I know 4 to the 3rd is 64. So to make it 1 over 64, it's going to be negative 3. E, 15 to what power is 15? That's going to be 1. And then for letter F, 8 to what power is 1? Well, anything to the 0 power is 1. So there's some rules here I want to walk through. I'm going to type these out so you can read them a little bit more clearly, but I'll return here in just a minute. All right, that's a little movie magic. Now we can see we have some details that we want to follow along with here for our additional properties. So the first one, log base b of 1 equals 0. Why is this true? Well, that's true because anything to the 0 power, and remember our answer is an exponent, equals 1. Number 2, I have log base b of b equals 1. Why is that true? Because anything to the first power is itself, right? This is an exponent here, so if I raise b to the first power, I get b, whatever b is. 3 and 4 are our inverse properties. Of all the things we talk about today, these are the two that trip the most people up. So the big idea here, if I look at number 3, it's really telling me, it's asking me b to what power, right? That's the question a log asks, equals b to the x, right? That's the term we're trying to figure the logarithm of. Well, as you can see here, this question mark should be x. So really, let's zoom in here. These two components, the log base b and the b, effectively undo one another, okay? And the same is true on number 4. I have b raised to the power of log base b of x. Well, let's do a different color. These two pieces undo one another, right? This will sound confusing, but let me just talk through it. This exponent here, okay, this exponent right here is a number. It's the number that when I raise b to this power, I get x as a result. Well, what I'm going to do is take b and raise it to the power that results in me getting x as a result. In simpler terms, the base and the log with the same base as an exponent undo one another. So all I'm left with is this x being here. Similarly, this x is here. The last couple rules, if b to the x equals b to the y, then those exponents must be the same. And finally, if no base is indicated, we assume it's base 10. We discussed that a little bit earlier. So there are 6 problems here. I am going to work through them myself, but I'd like you to try them first. So go ahead, pause the video, and check your answers here in just a minute. All right, let's finish up these examples. So on part A, we have the log, and it looks like there's no base there. But remember our rule from above, if no base is given, we assume that it is 10. So really what we have is log base 10 of 10 to the 6th. Well, that log base of 10 and the exponent base of 10, sorry about that, undo one another. So I am left with a final answer of 6. On part B, one thing that I notice immediately is that my log base is 3 and that my exponent base is 3. They will undo each other, and I'm left with just the x from the exponent. Over here on part C, it looks similar to part D, but not quite. What what's different here is that this base does not match this base here. But if we're clever about our numbers, we know that 81 is a power of 3. Specifically, we know that 81 is 3 to the 4th power. So we can rewrite 81 as 3 to the 4th power. Then we can use our exponent rules to multiply 4 and x together and rewrite this whole problem as log base 3 of 3 to the 4x. Our log base and our exponent bases cancel, and I get 4x as a result. Down to the bottom row. Here, we can trust our instincts, right? We have a log base 7 on both sides of our equation. So that means that the numbers here must be the same, right? We're performing the same operation on each of them. So I set them equal. 2x plus 1 equals 5. Solve for x. X equals 2. E behaves similarly. I know that I'm taking the log of 8y and the log of 5 on both sides of the equation. So I go ahead and I set 8y equal to 5, solve, and y equals 5/8. And finally, I have another problem where the exponential base and the log base are the same. They cancel each other out, and I'm left with 3x. Good work. I appreciate your patience, and please let me know if you have any questions about anything you saw today.